Welcome to our quantum deep dive. Today we're plunging into one of the universe's most elusive mysteries, the Axino. This hypothetical elementary particle could hold the key to understanding dark matter and perhaps even the very fabric of our cosmos.
And the foundation for our deep dive today comes from the insightful work of Jorgo Schneppe, particularly his comprehensive essay on the Axino as a, hypothetical particle of supersymmetry.
Okay, let's unpack this then. Our mission is to extract the crucial, nuanced insights from Schneppe's rigorous analysis. We want to explore what an Axino actually is, why its existence would, profoundly impact our understanding of the universe, and how scientists are attempting to find something so incredibly faint. Get ready for some genuine aha moments, because this journey really connects the smallest theoretical particles to the largest observed structures we see. So, to start, maybe for our listeners who follow particle physics, how would you define an Axino beyond just hypothetical particle? What's its fundamental basis?
Right. Well, at its core, the Axino is theorized to be the supersymmetric partner of the axion. But to really appreciate its significance, we probably need to quickly step back and contextualize its counterpart first, the axion.
Right, the axion.
That name comes up a lot. It's often discussed as a rather elegant solution to a persistent puzzle in particle physics, isn't it?
Precisely. The axion was originally proposed to solve what's known as the strong CP problem. Now, for those familiar with the standard model, fundamental forces operate with certain symmetries. The strong CP problem basically arises because, theoretically, the strong nuclear force should allow for a violation of charge parity symmetry. Imagine a fundamental process that doesn't behave identically to its mirror image. That's a rare and profound anomaly in physics.
Okay, so if nature fundamentally prefers symmetry, this strong CP problem is like a deep cosmic imbalance that needs explaining. And the axion is the proposed fix. It restores that balance somehow. That's the elegant idea, yes. The axion acts as a dynamic field. It naturally suppresses this theoretical CP violating term, essentially ensuring the strong force maintains the expected symmetry. This is actually crucial for understanding why our universe has more matter than antimatter. It's a very specific theoretical necessity.
Understood. So it's deeply motivated. Now, how does supersymmetry, or CUSY, bring the Axino into this picture?
Well, CUSY postulates that for every known particle in the standard model, there exists a superpartner with a different quantum spin. So, force-carrying bosons, which have integer spins, they'd have fermionic partners with half-integer spins, and matter-forming fermions would have bosonic partners. It essentially doubles the particle zoo, suggesting a deeper symmetry.
So, okay, if the axion, which is a boson, exists to solve the strong CP problem, then according to CUSY, there must also be a fermionic superaxion, and that's our Axino.
Exactly. The Axino would be a fermion, like an electron or a quark. And what's particularly intriguing, as Schneppe emphasizes in his work, is the strong possibility that the Axino could be the lightest supersymmetric particle, the LSP.
The LSP, right. And what's the critical implication if the Axino is indeed the LSP?
Well, if the Axino is the lightest supersymmetric particle, it means it would be stable.
Ah.
And this is a crucial, absolutely non-negotiable criterion for any dark matter candidate, because only stable particles can survive for billions of years and accumulate into the vast, unseen amounts of dark matter that, cosmologists observe holding galaxies together.
Wow. So the Axino, stable, invisible, born from elegant theory, and it could literally be the unseen scaffolding of the entire universe. That's really something to think about. But, okay, given how weakly it interacts, the idea of actually detecting an Axino seems incredibly daunting. How are scientists even approaching this? It sounds like searching for that needle in a cosmic haystack, but maybe the needle is invisible too.
That's exactly the grand challenge. Axinos are exceptionally difficult to detect precisely because they interact so incredibly weakly with, ordinary matter. But Schneppe's work, and others, highlights several really ingenious strategies researchers are pursuing.
Okay, what are these strategies? How do they plan to make the invisible, maybe not visible, but detectable?
So one approach involves searching for astrophysical signatures.
Right.
While axions are stable if they're the LSP, if they were somehow to decay, maybe in very rare scenarios or through interactions, they could potentially emit characteristic X-rays or gamma rays. And we might be able to detect those with highly sensitive space telescopes.
Right, like cosmic forensics.
Yeah.
Looking for faint energy signals from deep space. What else?
Another method is trying to produce axinos in particle accelerators. When protons collide at extremely high energies, like at the LHC at CERN,
Yeah.
the conditions might just might be right to generate these elusive particles that wouldn't be seen directly, but they could leave a tiny indirect signature, like missing energy.
Like a controlled mini Big Bang, hoping to catch a glimpse of something new leaving the scene. And is there anything beyond that? Direct detection, maybe?
Yes, that's the most ambitious goal. Direct detection. This involves building ultra-sensitive detectors, often deep underground, to shield them. They're designed to measure the minute recoil energy that would occur if an Axino, just one, happened to collide with an atomic nucleus inside the detector.
Wow. That's pushing technology to its absolute limits. It really underscores how fundamental this search is for physics.
It really is the potential discovery. It wouldn't just be another particle. It would be an absolute sensation, genuinely opening new chapters in physics and cosmology.
I believe it. Now, before we get too deep into the detection tech, I'm really interested in the broader impact. How does Yorgo Schneeppert specifically frame the implications? What does his work suggest about the Axino's role?
Right, Schneeppert doesn't just say it could be dark matter. His work is more specific. He theorizes how if the Axino falls within a particular mass range, it could uniquely address challenges like the small-scale crisis in cosmology.
Yeah, the issue with dwarf galaxies not matching standard cold dark matter models.
Exactly. Current models sometimes struggle there. Schneeppert shows how axinos, with certain properties, might resolve this discrepancy. That would fundamentally reshape our understanding of how galaxies actually form and evolve.
That's a really precise, testable insight. It's not just a candidate, it's a potential problem solver. And you mentioned he connects it to the cosmic microwave background too, right? The Big Bang's afterglow.
Precisely. He illustrates how axinos, if they were around in the early universe in large numbers, could have impacted the CMB. Their presence and properties would have left distinctive, subtle temperature fluctuations in that background radiation, like a unique fingerprint.
Fascinating. A signature from the dawn of time. And his work, I assume, clarifies how finding the Axino links to finding COSY itself.
Yes, that's a logical consequence, naturally, since it's a hypothetical superpartner of the axion. What's especially intriguing in Schneeppert's perspective is the possibility, maybe even a likelihood, of finding evidence for the Axino before we directly confirm other supersymmetric particles.
Really?
Yeah. It would offer indirect but incredibly compelling proof for CSY through a sort of backdoor.
Wow, that would be huge. Finding CSY indirectly via the Axino.
So what specific properties does Schneeppert's work emphasize that make the Axinos so uniquely suited for these roles? Is it just being light and stable?
Well, those are key, but Schneeppert's work delves deeper. It looks into the Axino's production mechanism in the very early universe. Depending on whether it arose from thermal processes or maybe later phase transitions, that predictably influences its final mass and how abundant it would be today.
Oh, okay.
And understanding that allows for much more precise predictions about its gravitational effects and how weakly it interacts. So it's not just what it is, but how it got here that helps make these precise predictions. How does he picture its role in structure formation then, back in the early universe?
Schneeppert argues that axions would have originated in, significant numbers within the hot, dense plasma right after the Big Bang. As the universe expanded and cooled, these axinos, being weakly interacting and stable, would have started to clump together due to gravity, even before normal matter could. They would have acted as the initial seed cells, or gravitational wells.
Okay.
And then ordinary visible matter would fall into these wells, guiding the formation of the first stars, galaxies, and the large-scale cosmic web we see.
So literally the invisible hand shaping the cosmos from the start. And we could potentially see evidence of this in the CMB, as you said. How would we pick out that specific Axino fingerprint?
His work shows that axinos with certain properties would modify the detailed patterns of temperature fluctuations, the anisotropies in the CMB, in very specific ways. It would be different from the patterns expected from, say, other dark matter candidates like WIMPs. Modern telescopes like Planck and future ones are becoming sensitive enough to potentially distinguish these subtle variations.
So we could effectively see the Axino's influence in the universe's oldest light. That really sounds like we're getting close to being able to test these ideas. Schneeppert's work seems to provide a solid theoretical roadmap.
Absolutely. It delivers a variety of concrete, testable hypotheses. It gives experimentalists and astronomers specific targets and signatures to actually look for.
Now, this sounds like a challenge that absolutely requires a global effort. Beyond the obvious, immense technical hurdles, what other specific challenges does Schneeppert highlight in the search?
Well, beyond the sheer difficulty of building detectors sensitive enough, Schneppet also emphasizes the challenge of precisely modeling the Axino properties theoretically. We need really highly accurate predictions for its exact mass range, its extremely weak interaction strengths, its precise formation mechanisms.
Right.
Without those precise models guiding the search, our experiments and observations would be, well, much less efficient. Like shooting in the dark, really.
So the theoretical work, like Schneppet's, is just as critical as building the detectors. You need to know exactly what faint signal you're looking for and where. Are there concrete plans for these advanced detectors already underway?
Oh, yes. Various research groups around the world are actively developing new detector concepts. Some are specifically optimized to search for those minute recoil signals from potential axononucleus interactions. It shows the commitment.
That's promising. And given the scale of this, Schneppet's work also talks about international cooperation, doesn't it?
Yes, his essay definitely articulates that. Such a complex, boundary-pushing task simply cannot be tackled by one group or one country alone. It demands a truly global scientific effort.
So what forms does this collaboration take? Is it just researchers sharing data or more integrated projects?
It's really both. There's a constant, pretty robust exchange of data, research findings, publications. Conferences and journals are critical for keeping everyone informed.
Like a giant puzzle where everyone contributes pieces.
That's a good way to put it. But there are also large, joint research projects where multinational teams work very closely together. A prime example is the ongoing search for new physics, which includes looking for potential Axino signatures at the Large Hadron Collider at CERN.
The LHC, the biggest machine humanity has ever built, searching for potentially the smallest, most elusive particles. That contrast is just amazing.
It is quite fascinating, isn't it? The pursuit of the Axino really embodies how fundamental physics pushes the very boundaries of our ingenuity and our technology.
This whole deep dive, it really fills me with wonder. Just the intricate complexity, the hidden beauty of nature. What concrete hopes do you personally have for Axino research? Based on Schneppet's insights and what's happening now, do you think we'll actually discover it soon?
Well, predicting timelines in fundamental physics is always tricky, let's be honest. But the rapid advancements we're seeing in detector technology, plus the increasingly precise measurements of the CMB that Schneppet's work connects to, it certainly makes me optimistic. Each new generation of experiments gets us closer. We either find it or we significantly constrain its possible properties, which is also valuable information.
That sounds hopeful. And if we did find it, what impact would that definitive discovery have on our sort of worldview, our understanding of the universe?
Oh, the implications would be transformative, really. Imagine if we could definitively prove that the Axino is the main component of dark matter. That wouldn't just revolutionize our understanding of how cosmic structures formed. It would also likely confirm the existence of supersymmetry, giving us a much more complete picture of fundamental particles and forces. It connects so much.
Right. So beyond solving the dark matter puzzle, what other big mysteries could the Axino help unlock?
Well, confirming CSY would be massive in itself. But the Axino could also provide profound new insights into the very earliest moments of the universe. We're talking the first fractions of a second after the Big Bang, a period still shrouded in immense mystery. It might even offer clues down the line to understanding quantum gravity, which is one of the biggest unsolved problems in physics.
The Axino, potentially a key to unlocking some of the universe's absolute deepest secrets. That's just an incredibly exciting perspective.
Absolutely. The exploration of the Axino is, well, it's an adventure. It leads us right to the limits of our knowledge, and maybe even a little beyond.
Well, a huge thank you to Jorgo Schneppet for his pioneering work. It's really provided us with such a fascinating and detailed insight into this whole Axino world.
Yes, his meticulous explanations, they've been really instrumental in helping us, and hopefully you listening, better understand the profound significance and potential of this particle. And for anyone who wants to dive even deeper into his specific hypotheses and research, we absolutely recommend exploring his website. That's schnepppat.de.
That was our deep dive into the enigmatic world of the Axino. We hope you gained as much clarity and wonder as we did exploring this elusive particle. Until next time.